Let's look at our next example, 9.3.2. We want to use the simplex method to find the minimum value of w as a linear function of three variables, 2x1 plus 10x2 plus 8x3. That means we want to minimize w subject to the following constraints. The first constraint is x1 plus x2 plus x3 must be greater than or equal to 6. Second constraint, x2 plus 2x3 must be greater than or equal to 8. And the last constraint, negative x1 plus 2x2 and then plus 3x3 must be greater than or equal to 4. And we also have those non-negative constraints. All the x variables or all the variables must be non-negative. So we start off by writing the augmented matrix corresponds to this minimization problem. Again, this portion of the matrix, we got it from the coefficient of each variable. So the first column contains all the coefficients of the variable s1 in each constraint. 1, 1, and negative 1. So 1, there's no s1 out of the second constraint, so you get 0 s1 right over there. Negative s1, so 1, 0, negative 1. The second column over here out of this portion contains all the coefficients of x2 out of each constraint, 1, 1, and 2. We get them from 1, which is the coefficient of the first of x2 out of the first equation. 1 and 2, 1, 1, and 2, 1, 1, and 2. The third column contains all the coefficients of x3, 1, 2, 2. And that portion, you get it from all the constant terms on the right-hand side of each constraint, 6, 8, and 4. Okay? The bottom row, you get this part from the coefficient of the variable in your objective function, 2, 10, and 8. Okay? And you put 0 in that spot. To solve this minimization problem by using the simplex technique, so we first find the transpose of this matrix. After we have got the transpose, this is the transpose of that matrix, okay? We're gonna get the dual maximization problem. So I'm going to be using the variables y1, y2, and y3. Okay, so out of the first row, you get the first constraint to your maximization problem. y1 minus y3 lesser than or equals 2. Okay, out of the second row of your transpose matrix, you get the second constraint of your dual maximization problem. y1 plus y2 plus 2y3 must be lesser than or equal to 10, which is this guy. Out of the third row, you get the third constraint of your dual maximization problem. y1 plus 2y2 plus 2y3 must be lesser than or equal to 8, which is that constraint. Out of the bottom row, you get the new objective function. That means you want to maximize the variable z, which is 6 times y1 plus 8 times y2, and then plus 4 times y3. So the coefficient of y1 is 6, coefficient of y2 is 8, and coefficient of y3 in your z equation is 4. So we want to maximize this guy subject to those three constraints. And we still have the non-negative constraints as well. And since there are three constraints out of this problem, the dual maximization problem, so three constraints, it means that we have to add how many slack variables? 3 slack variables. So I'm going to name my slack variables, the three of them, as S1, S2, and S3 as usual. So by adding the three slack variables, S1, S2, and S3, I get the maximization problem as this problem. okay? So we want to maximize z as that linear function of three variables, y1, y2, and y3, subject to all the constraints, okay? By adding the three slack variables s1, s2, and s3, those three inequality constraints will be changed to equal constraints, so will be with the equal sign, all right? So with that maximization problem, after we have added the slack variables, we can then get the initial tableau, okay? Let me again write the variables correspond to each column. The first column is for the variable y1, second column is for the variable y2, third column is for the variable y3, and the next three columns are for the slack variable s1, s2, and s3 respectively. So S1, S2, and S3. The next column is for the z variable, and the last column just contains all the constant term on our right hand side. Okay, again, from your first row, you get y1, no y2. That's why your y2 here is 0 in that column. Negative y3, so negative 1 goes there. You get 1 S1, so 1 goes here. No S2 and S3 variables, that's why you have 2, 0 on that two spots. Okay, no z variable, that's why you get 0 over here. The constant term on the right hand side is a 2, so you put 2 right there. Same idea for the second row. You get 1 y1, 1 y2, and 2 y3. So 1, 1, 2 go there. No S1 variable out of your second constraint, so this is 0. There's one S2 in your second constraint, so you put 1 right here. No S3, no z variable out of your second constraint, and the right hand side is a 10. So 10 goes there. Out of the third constraint, okay, the third equation, you get 1 y1, 2 y2, 2 y3. 0 S1, there's no S1 in here, no S2 in there, but you get 1 S3, so you put 1 right over there in that column for S3. No z variable, so 0 goes here, and the right hand side is 8. Okay, for the objective function, you put the coefficients of y1, y2, y3 in the bottom row, but before you do so, you have to rewrite your objective function. So I move everything to the left hand side, and I get negative 6y1 minus 8y2 minus 4y3 plus z equals 0. Move everything to the left hand side. Okay, so the coefficient of y1 is negative 6, that's why negative 6 is shown at this spot. Coefficient of y2 is negative 8, that's why you have negative 8 right over there in the y2 column. Coefficient of y3 is negative 4. You have no slack variables in the objective function at all. So S1, S2, and S3 are all 0, the coefficient of them. Okay. Z, you get 1z, so you put 1 right over there. And the right hand side of that objective function is now 0. You put 0 in that spot. And that is your initial tableau. So that is our initial tableau. Let me put down the non-basic variables out of that table. So the non-basic variables are S1, S2, and S3, our slack variables. So again, that column is for Y1, Y2, Y3, S1, S2, S3, Z, and B. With the simplex method, we look at the bottom row and search for the most negative entry. The most negative entry is negative 8. That is the most negative entry. So that negative 8 falls into the second column, which is the column of y2. So we know that y2 is going to be the entering variable. To find the departing variable, we need to find a ratio of b over y2 in each row. There are 3 rows of the constraint. But the first row we cannot find a ratio because the ratio of b over y2 is not defined because y2 is 0 in that spot. So we only compute the ratio of the second row and the third row. So the ratio of the second row, we divide 10 by 1, and the ratio of the third row, we divide 8 by 2. So compute the ratio. We compute the ratio to get the departing variable. So divide 10 by 1, the ratio is 10. And the other ratio is divide 8 by 2, which is 4. And then we compare between those two ratios and find the smallest non-negative number. Between 10 and 4, 4 is smaller, and that is the smallest non-negative ratio. We get that smallest non-negative ratio from the third row. So it means that your S3 is going to be the departing variable out of this step. So I'm going to put down saying that this is departing. And this guy will be our pivot element. So pivot element. After I've known that that is my pivot element, I'll just go ahead, divide the third row of my tableau by 2 just to create a leading one, and use that leading one or that pivot element to get rid of everything else in that column. You don't have to get rid of this guy because it is already 0. So you only use that pivot element to get rid of this guy and that guy. I'm going to put my work in the next slide, okay? So I'll bring this table or that matrix and put it over here. You can see that it's just exact same thing over there. I put it here, and this is my pivot element. I'm gonna divide throughout the third row by 2 just to create a leading one. Okay, I'm gonna put the highlight. So after divide the second row by 2, the third row, okay, divide the third row by 2. The first row, the second row, and the fourth row remain the same. So only the third row will be changed, and I divide throughout by 2. I get that resulting row. The other 3 rows remain the same. After I've got that leading one that I put the pink color cover it, I'll use it to get rid of that one. Okay, that one that appear in the same column as my pivot element. So to get rid of that guy, I perform R2 minus R3. Okay, and to get rid of that negative 8, I perform R4 plus 8 R3. And then I go ahead perform those 2 row operations and I get this resulting matrix. Now I'm going to take care of the simplex method by bringing this table and then check out and see the next entering variable and the next departing variable as usual in the next step. So let's look at the next slide. I bring that matrix again, okay? We have to update our non-basic variable. Previously, in our first step, S3 has departed already, and we replace it with the entering variable, which is Y2. So the non-basic variables are now S1, S2, and the entering with variable was Y2, so Y2 goes there. We haven't reached the maximum value of Z yet, but at this step, you have the maximum of Z as 32, but it's not the maximum yet because you still have negative entry out of the bottom row. Okay, look throughout the bottom row. The most negative entry, actually we have just one negative entry out of the bottom row, which is this guy, and that is going to be our next entering variable. So entering. Okay, gonna enter that Y1. That is for Y1 if you want to label it Y1. Okay, by seeing the entering variable, we have to again find out the departing variable. So we will continue finding the ratios, okay? Compute the ratios. There are 3 rows or 3 constraints. None of them is 0 in that column, so we have to compute 3 ratios altogether. The first ratio is divide 2 by 1. The second ratio is divide 6 by 1/2. And the next ratio is divide 4 by 1/2. So the first ratio is 2 divided by 1, which is 2. The next ratio is 6 divided by 1/2, and that gives 12. And the next ratio is divide this b by y1. I get 4 divided by 1/2, and that gives me 8. I need to compare all those 3 ratios. We want to look up for the smallest non-negative ratio, and this is the smallest non-negative ratio. 2 is the smallest non-negative ratio, and that 2, I got it by finding the ratio of b and y1 in the first row. It means that my next pivot number is this guy, and that implies my S1 is the next departing variable. S1 is the departing variable. So S1 will be departing. Okay, because the ratio 2, which is the smallest non-negative ratio, I got it from the first row. And Y1 is the entering variable, and S1 is the departing variable. With that pivot element, I'll get rid of all those 3 numbers underneath it. So I perform Gaussian elimination to get rid of all those 3 guys. I'm going to show you in the next slide. Okay, I bring this matrix, put it to the left, and I'm going to put pink color, cover my pivot element. To get rid of this guy, we perform R2 minus 1/2 R1. To get rid of this guy, we perform R3 minus 1/2 R1. And to get rid of negative 2, that is in the 4th row, we perform R4 plus 2 R1. And this is the resulting matrix after I have performed those 3 row operations. So I'm going to bring that matrix to write down as my simplex tableau, okay? And I'm going to update my non-basic variable. If you cannot remember, you can go back. Previous step, the non-basic variables were S1, S2, and Y2, but S1 has departed and updated with the entering variable Y1. So the non-basic variable in the first row is going to be Y1. So we get the non-basic variables as Y1, S2, and Y2. Y1, S2, and Y2. Okay? Now we look at our bottom row. There's no negative entry anymore in our bottom row. It implies that we have reached our maximum value of z, and 36 is the maximum value of z. That is the maximum value of z. And that maximum value of z occurs when y1 is 2, y2 is 3, and y3 is 0, okay? We don't have to have y3, okay? The maximum value of z occurs when y1 is 1, y2 is 3, and y3 is 0. We can also read the answer or the minimum value of w from this final table. So we say that 36 also the minimum value of w, and that minimum occurs when x1 is 2, x2 is 0, and x3 is 4. Okay, So the minimum value of W occurs when x1 is 2, x2 is 0, and x3 is 4.